All right, yeah, I'm going to talk about biofluorescent particle counting. Just quick, who's heard of it before? We got a few, and we're kind of halfway there. I'm glad, Tim, you raised your hand. Thanks. So yeah, we're going to discuss this as an option for meeting the requirements of Annex 1. Because really one of the things that Annex 1 is talking about, and Lena's presentation at the end of the day yesterday really sort of led us into this, is a push for modernization. As it's stated up there, use of isolator, robotic systems, continuous monitoring systems, really to assist in the rapid detection of potential contaminants. And really this modernization idea that they want people to move to this goes all the way back to the initial concept letter from 2015 when they said that they were planning on updating Annex 1. In fact, in there, I think they said they wanted to encourage the embrace of new technologies, which is definitely a change from really, especially how people interpreted the previous version of Annex 1. But why are they looking for this change in the industry? I mean, there's really two reasons. One's improved quality. They see other industries have embraced new technologies, and it has allowed them to vastly improve the quality of the products that they produce. And then the other one, which has really been an ongoing issue, but really only got magnified during the pandemic with drug shortages out there. So if you can consistently produce a high quality product, you can avoid some of those drug shortages out in the field. So as was even pointed out in that previous comment that I took out of the annex there, environmental monitoring is one of the aspects that they are encouraging you to try to modernize over what has been a very old technique, the traditional microbiological methods. And so viable air testing is one of those areas that they are pushing for modernization. And we can see it in a couple sections again that I've taken out of Annex 1 there, where it's looking for continuous viable air monitoring in grade A zones. And this is really the application I'll be focusing on here, is the use of biofluorescent particle counting in the grade A area. They also are looking to reduce risk caused by the intervention of monitoring operations. Because really in modern isolators, the technology is so good at creating a good, clean environment that the greatest risk often to the process is the environmental monitoring to show that it's clean. So it's kind of a contradiction there that they'd like to obviously be avoided. And then they encourage the adoption of suitable alternative monitoring systems that will expedite the detection and reduce the risk to product. I mean, what are they really looking for here? They're looking for something that can give you process control, because that's something you don't currently get using the traditional methods that are in place now. And then, of course, reduce risk. We heard that, and Lena, I think she said risk was referred to over 100 times or something in Annex 1. So it definitely is something that comes up here as well to really drive that reduced risk to your product from your environmental monitoring. So let's go through this. I don't know if you probably aren't all microbiologists. You may not have lived doing this every day like I did for 20 years of my life. So we'll kind of just do a quick review of what monitoring looks like today for the most part in your grade A environment. And it's currently, it's a very manual process, as you'll see. Takes a while to get results. And your samples tend to represent large portions of your batch because they're represent a large period of time. And we'll see how that goes. So we heard Karina talk about active air sampling. That's still the common, one of the common methods used. And how that generally is used is that they'll bookend the batch. So they'll take their active air sample at the beginning of the batch to represent that, hey, when we started, looks like everything was working properly, we were in a state of control. And then after the batch is over, they'll take an active air sample again at that time to show, yep, everything is still working, nothing broke down that we see contamination at the end. And that's because these, when you're sampling with an active air sampler, they are tend to be fairly short sample times that you can sample because drawing that air in, like she talked about, will dry out the plate so you can only sample for a certain amount of time. So unless you go in to change plates very often, which you want to avoid doing all those interventions, you can't really do active air sampling throughout your whole process. There are some ways and there are some improvements that are getting out there using some slit to auger samplers and stuff that make it possible. But for most people, it's generally beginning and end, maybe once or twice during the middle if they have very long batches. But again, these will represent large periods of time of your batch. So during the batch then is usually left for settle plates to do that sampling. So this is just passive sampling. You just set the plate out, let it sample for 4 hours. Sometimes if there's higher flow rates in the isolator or something, it may be shorter periods of that than that time. And so they may be switching these out on a fairly regular basis, which will cause some interruptions and more interventions into your process. Once they sample those, they have to take those back to the lab, put them in an incubator, and then they're going to incubate for 2 to 7 days. They may go in an incubator at one temperature, and then after a day or two, move to a different incubator. Different places have different incubation schemes that they've validated to try to recover as many organisms as they can. And then after that incubation time is up, they'll take those plates out and they'll look for our colony forming units growing on there, our little dots on there. So this is where the particle has landed. There's something culturable on there that continues to replicate until there's enough of them on there that you can actually see the colony, and then you can count those. So if we look at it through the viewpoint of the process control and risk that I talked about that Annex 1 was really driving towards, let's look at the issues that we see using these traditional methods. Well, those bookend samples, or even if you take 1 or 2 in the middle, doesn't really indicate any control in your process. You don't know what was going on, why you were actually running things. You just know beginning and end things were all right. Things could have gone haywire during the middle, and you have no indication of that from those samples. So you do have the settle plates that were sitting in there to continuously monitor throughout the process, but settle plates are going to have poor recoveries compared to your active sampling. I think Karina used the example yesterday that the active air sampler, she used the analogy, it's like a car driving fast and it can't make that turn, so it crashes into the wall. That's the particles going and they're crashing into the plate in the active air sampler. Well, settle plates work much the same way, except for instead of air being actively drawn through, it's relying on the air flow in the room to move those particles towards the plate. So instead of a speeding car crashing into the wall, it's more like the queue at the airport probably. So you know, you're not very likely to not be able to make that turn. And then, as Morgan showed on some of those, if that air is not moving straight up and down anyways and turning away, none of those particles may even be getting close to the plate. And so, you know, you can miss a lot with settle plates, but you know, it's what people had. It was the best they could do to at least, you know, try to catch something that may be there. Settle plates also require a lot of manual manipulation. You have to open it and set it out and close it back up, stack them up, bring them back to the lab, put them in an incubator. So that they are prone to contamination. Oftentimes, there'll be, you know, investigations when they have excursions, and it'll be found to be laboratory error in handling or something that they'll attribute any growth on these plates to. Anyways, and then as I said, these represent 4 hours of time in your batch often, so that's putting a lot of your batch at risk based off of this settle plate, because you don't know if whatever landed on there that grew into a colony landed the first second you put it in there, or, you know, 4 hours into it, or anywhere in between. So you have to consider that whole portion of your batch to have been at risk. Then your results are delayed for days. Really probably could have moved that one to the top or just removed everything else, because if you have to wait days, it has no influence over your process whatsoever. It becomes a batch test later on that you can only retrospectively look back on your batch to see if there was any impact to it at all. So you cannot take any mitigated actions based off of that to try to protect your batch while you are processing it. And then, as stated, the whole batch or a large portion of it, whether it's the active sample or the settle plates, you need to consider that whole large portion of your batch at risk. Then the risk to the process, well, it's a lot of manual interventions. As I said, even settle plates, I mean, we did see MBV has a little robot now, so maybe you can cut some of those interventions out. Even with that, you're still loading a lot of equipment and media into your grade A environment, which increases your risk. I mean, you see bags and bags of media, and you have to, you know, hang those up, and they get, you know, put in there for your VHP cycle. But as you add more and more surfaces with crinkles and bags and stuff, and VHP has to have direct contact to be effective, you're just putting yourself at risk. And it's media. You're putting things that is supposed to make microorganisms grow into your clean environment, and you know, be best to avoid having to bring those into your aseptic environment. So what's the alternative here? Biofluorescent particle counting is a truly alternative method. You know, you hear people talk about rapid microbiological methods or alternative. Generally view rapid method as still being a growth-based method, but it allows you to count the colonies faster than waiting for it to grow to be visibly, you know, with the human eye. Whereas an alternative uses something other than growth to determine if that particle is viable or not. So it doesn't rely on growth. What BFPC relies on is this method known as laser-induced fluorescence, or LIF. And this is really based on the fluorescence of molecules that are in growing organisms, because they're molecules associated with cell metabolism, so it makes them a good indicator for viability. So we can kind of see down here what's going on in the instrument. We have a particle that will pass through a laser beam, and then if it just scatters that light, and so if it's all the same wavelength as the laser light, we know that's likely not a viable particle. But if we send that particle through the laser, and you get some light scatter, but you also get light that now has longer wavelengths, that's because it's fluorescing. It's absorbing some of that light energy and losing some of it, and then it gets re-emitted at longer wavelengths of light. So if we put sensors in there to look for the fluorescence and the light scatter, we can determine whether a particle is viable or not. But in operation, it really operates like a standard particle counter would. You hook it up to the system, it runs continuously, it samples every minute or whatever interval you set it at, so it's fully automated. There are no interventions with it. You don't have to deal with any plates or anything like that, and you're getting your results in real time, just like you would a standard particle counter. In fact, instruments will have both a standard particle counter in it and then the biofluorescence particle counter in it, and so you'll get both counts at the same time. You'll get your total particle count and your viable particle count, or autofluorescing units is sort of the general term that's come to be accepted in industry for that, and it's abbreviated AFU, sounds like CFU, the colony forming unit, just to kind of make it easy for people to transition from one to the other. But what it is counting the number of particles that could be viable, or at least optically appear to be viable. So now let's look at that sort of process control risk lenses we were looking at the previous growth-based methods with. Let's look at BFPC through those lenses. So you obviously have the improved process control then, because you are actively sampling throughout your process, and you know what the state of control is, and that allows you to take immediate action. So you see a spike in viable particles, you can immediately stop your fill line, your production. You can segregate those. You can, if you know that there was some action that caused it to go out, you can take immediate corrective actions to bring it back into a state of control. You are continuously monitoring, so you will know if it's back into a state of control and it's safe to start up and continue on with your batch. Or if it's something you can't fix, you can stop your batch altogether and prevent making a whole bunch of drug that you have to throw out. So it allows for that immediate action to really limit any impact that contamination could have on your batch. And then no risk to the process. Again, it's fully automated. You don't have any manual interventions. Again, just think about it running just like a particle counter. You don't do anything with that. It's just running all on its own. You never look at it until you get an alarm, and that's it. There's no actions you need to take to actually do the sampling. And then almost all monitoring equipment in media is removed from the grade A environment. Previously, you had to have an isokinetic probe for your particle counting. You needed your active air sampling head. You needed a stand for your settle plates to go on. You had to bring in those bags and bags and bags of media that all line up and hang up during your VHP cycle. All that's removed from your process here, removing a great deal of risk to your process. So some further support for implementing things such as BFPC in Annex 1 talks about monitoring systems that scientifically sound alternative methods that optimized detection should be included, or at least you should assess the feasibility of it. Looking for the expedite detection of micro-contamination, reduce risk again. Even in the table there where they've discussed using the traditional microbiological methods, and they give you limits for what, how many CFUs you can have on your settle plate, on your active air sample plates. Underneath that table, they point out there that other methods can be used. New technologies are used that present results in a manner different from CFU can be used. So again, they're opening the door up for people to use alternative methods. All right, there's some additional benefits to using BFPC, even more than what I've already covered for meeting the Annex 1. Big one is reduced downtime. Probably without that, it would be hard to get new technologies in because that's really where companies save a lot of money on their reduced downtime, because if you are changing out settle plates during your batches in your grade A, you need to stop your line, change those plates out if you're taking an active air sample at that time as well. That makes it even longer, and if you have a high throughput filling machine that's producing 600, 800, 1,000 vials per minute, every minute that you're down is costing you a lot of money. Improved data integrity. Besides the risk to your process from all those manual interventions and manual parts of the operation of doing this traditional monitoring, there's risk for data integrity there that human error can creep into it, whether it's the handling and you contaminate the plate, which makes it inaccurate, so you have bad data, or just you're manually reading the plates, and that's a subjective activity a lot of the time, because one person could read 3 colonies on there and someone else might not be able to see that one really small one, and they only count 2. That type of thing. So it is a very subjective test that it is prone to errors as well, or at least inconsistencies. So greatly improve your data integrity by having this fully automated system. Again, kind of already brought this one up, but really you just have that one probe inside your isolator. It certainly helps out the isolator manufacturers or filling line manufacturers to not have to work around all this monitoring equipment that could be in the way of their process. No plates in the grade A environment, besides, again, the risk of having them in there. Something that early users of this technology have commented on is how nice it is to not have all these bags of media that's up in their line of sight and blocking their view, and they can see so much better. Again, working with isolator manufacturers, they can optimize where their glove port's going. Instead of making it so that they can have these glove ports where they have to go in, where they to switch settle plates or work the active air sampler, and maybe you can still reach over to break up a vial jam or something. They can put them in more strategic places for the actual process rather than for monitoring. So they can really optimize where glove ports go and maybe even remove some of them from the process. Again, removing all those materials makes VHP validation much easier if you're removing a lot of those surfaces inside there, and like I said, not bags of media blocking the airflow as it flows around. So it makes getting consistent concentration of VHP in your isolator much easier. Just supports new technology such as gloveless isolators. Again, unless you go to great efforts to roboticize these methods, it's otherwise it's very difficult to do settle plates and active air sampling in a completely gloveless isolator. And then pharma 4.0 or even 5.0 as they're talking about now, which really relies on immediate feedback into the system. So again, that goes into the whole process control part of it. Pharma 4.0 is really automating that process control. So unless you're getting real-time results, it just doesn't work in that paradigm. All right, some implementation considerations. If you are looking to install a BFPC, again, it is a particle counter, and it's taking your total particle counts as well, so you want to make sure you have sufficient flow rate, so that 28 liters per minute that's mentioned in Annex 1. And currently, at this point at least, on the particle collection, you want whatever method you have to have some way of collecting these particles so that you can try to get an identification. I believe Lena pointed that out in her presentation yesterday as well. And then installation, while I talk about, it's particle counter, think about it like a particle counter and how it operates and everything. It is, if we go back to a picture, there we go. It is a lot bigger than your remote particle counters that you're going to have on your isolator or RABS line. I mean, those little remote counters, probably fit in about this size compared to the size of the BioTrack. So you are going to have some considerations there for tubing, because it may not be able to fit nicely underneath your isolator. So you may have rather convoluted tubing configurations. You need to work with isolator filling line manufacturer to try to optimize those. And now Annex 1 is saying that those tubing configurations should be qualified. I won't go into too much more detail about it because Hasim's going to talk all about that here in a few minutes. But it is something that you definitely need to be aware of. And then, really, like I said, the key with this as well is you can really integrate it completely into your system, into your fill line and the isolator, so that if you do have an excursion, it can automatically stop your line and avoid really having us humans have to make decisions. So with that, I'd just like to thank you for spending a little time and learning about BFPC, since many of you had not heard of it before. And so we'll take any questions.
Are there any questions? Has anybody got any questions? Oh, lots of hands up. Right, here we go. I'll do you because you're nearest.
Thanks, Mike, for the presentation. Roland Turner from MBV. You gave us a lot of reasons why people should adopt it. Now, I think many people know that adoption of these technologies is super slow. Do you also know why this is happening?
Well, it has definitely been slow. Annex 1 has sped it up a lot because it was often mentioned as a roadblock that Annex 1 doesn't allow us to use something different. So this has sped it up a lot, and part of it is like any new technology, the regulators, and in fact the regulators have said to us, even both the EMA and FDA, yes, they want this to be successful, but they're conservative by nature, so initial, early adopters have had to do, fairly extensive testing. So we're hoping and expect that to sort of be reduced down as a handful of people get through it. It will get a little easier each time until it's the validation part is a little more cookie cutter. But that tends to be the slow point up to this point. Some of it is also working with the filling line manufacturers and isolator manufacturers to build it into their equipment rather than trying to retrofit it on, which takes more time and effort than it probably will in the future as well. But that same question can be asked of pretty much any new technology in the pharma world, especially on the testing side. Use the turbidimetric and chromogenic endotoxin testing as sort of an example. It seems like that came on really fast, but that took about 10, 15 years for adoption as well. So the fact that this has been out for 12 years is sort of speedy adoption for the pharmaceutical world.
Thank you. Next question.
Thanks. I think this, at the moment anyway, is more of an enhancement to an environmental monitoring program rather than a replacement of current environmental monitoring because of the need to speciate isolates, because that helps us identify what part of our process controls have failed or are weak. However, I was just wondering, because it is a biofluorescent method, I was going to say as well, there's that also, it would be useful because you're demonstrating what's normal for your process, so you're not going to have the tables that you comply with as you go on. So it's useful because it'll get people to think for themselves, perhaps, rather than just ticking boxes. But I just wanted to ask how this works with biologicals, for example, because the process themselves would generate particles that will fluoresce.
Yeah. All right. I'll try to cover all those. I mean, we do have we have someone now that has gotten approval, and they are operating completely, having replaced their active air sample and settle plates. So it is not in conjunction with. So it can be used as a full replacement for those. I think there was a second point there. No, I don't remember what that one was.
Just wondering about ATMPs and biological medicines.
Oh, yeah, biological, yeah. At this point, we haven't seen, so yes, there are other things that can fluoresce and cause false positives, and that is part of the validation process. Users look at the materials that they use to see if they could produce false positives or not. And at this point, we haven't had anyone have an issue with their product. Because there really is, on our unit, we have 2 fluorescence detectors and 1 size detector on there looking at each particle. So it's taking 3 measurements, feeding that into an algorithm, and that determines if it's viable or not. And so sometimes, some of these biologics, it could be that they're just big, and so they're not causing it, or the fluorescence is slightly different. Signal for those types of cells, but at this point, no, we haven't seen an issue with that. And now the third part of your question? Yeah, I got sidetracked. Yeah, well, if you think about it.
It's just the ability to, because we still.
Oh, yeah, speciation. Yeah.
That helps us identify what the likely frailties of our environment.
Yeah, and on our unit, as you saw there, we actually, down here, this little part here, the last part of the instrument, it uses you can install a Sartorius gelatin filter, which allows you to collect the particle and then place down media to try to speciate it if you get a hit. No. No, it gets through there and say it's no different than going through the tubing, going through the instrument, and then the reason why we went with the Sartorius gelatin filter is because that's been validated to sample for long periods of time without losing viability. So yes, now the method's more sensitive, and there's lots of things that aren't culturable. So you're probably not going to get anything to grow, even if you get a hit. But you do have the opportunity to. I am involved in a working group that has vendors of fluorescence instruments and members from the pharmaceutical industry in it. The modern microbial methods or M-Cube group, and we did recently write an article that was published in the PDA letter discussing that there's not actually a lot of value in trying to speciate if you're doing real-time viable air testing in grade A. There's a lot of value in it in your overall EM product program, but not necessarily for monitoring in grade A. Recommend you review that. It really our target audience was the FDA and EMA, but anyone else we can get on our side is helpful.
Any more questions from anyone? Oh, you just been.
Thank you. I think a lot of the questions I have you've answered. I do have one though, because I think you can identify a lot more with this system than you can with the agar plates, yeah, because not everything grows on the agar plates. So is that a risk? Because you mentioned one company has bought this and doesn't have any other systems on their line. So they'll be seeing potentially a lot more that they don't necessarily want to see, if you know what I mean. So how's that being addressed, do you know?
Yeah, well, part of it goes into that efficiency thing because yeah, I mean, actually, I've seen their numbers, and actually the frequency of hits is lower, but they're getting so many more data points that they get them, you know, time-wise much more frequently. But even with that, the cost of doing the investigation, which doesn't necessarily need to be as extensive as it was before when you're looking at whole batches and everything, is less than that loss of production time that they had in changing out settle plates and all that. So it's still a net positive for them, even if they have more of these events that they have to deal with.
Thanks.
It's just time for one more. Chris, you still got, yeah? I'll come to you.
I think my question was probably on a related point, and it goes back to what you were saying about integration with the systems and what goes on, is if you can integrate it into the filling system such that you can automate the response, the line stops because I don't have a grade A by definition, yes. There is something viable there, and it can auto restart when I'm now back in control and you can take the vials out. Is there a way that when you're then capturing samples on the agar filter, you can have effectively a timestamp by rolling when the impaction is, so you can say, that correlates to that hit, so it could be useful to you. And at the same time then, not really worry, because what we're worried about isn't that I'm getting the hits, it's that those hits had the potential to be a CFU, which meant my batch was implicated. This is exactly what the regulators were going for. Because it's integrated and I've stopped, there's no product risk, therefore there's no patient risk. But is there a way to have all of that data time-stamped and say, okay, this was the event, the line did stop, and I've taken the risk away, and this is the speciation, so investigation can tell me exactly where it came from, what it is.
Yeah, I mean the speciation really doesn't matter, because you have to assume anything you get could have been viable, whether it grew or not. You have to assume that there was a risk of it there. So whatever it tells you it was, if you did get it to grow and you were able to speciate it, really isn't going to change anything. Any organism is considered to be objectionable. So at that point, it doesn't qualify it as a good or bad hit or anything like that. The risk doesn't change to your product at all. So yes, that is sort of the argument of the regulators, is you need it for your root cause analysis, but really, especially the users that get into it, stop seeing the value in that anyways, because if you got a hit because someone reached in to do to break up a vial jam, you know that's what it was. You don't need to, oh, staph epidermidis came up 8 days later. Well, great, you know, doesn't really change anything in that aspect. And you moved on with your life. You've dispositioned your product. You've done all that. Yes, you could possibly tie it in if it's a bacillus to see, oh, I saw this bacillus over here. But that's where your broader EM program is going to catch that anyways. And they're still taking surface plates inside there. So if there is something like that, there's you know, just as good a chance that they're going to pick it up there and be able to match it up with where it was in their surrounding places. But it's more likely you're going to see, oh, yep, I see that in the D space, I see that in the C space, and then we got some in our B. Well, that's probably what got in the A. So yeah, it's those things where, like I said, that when you get into actually running and operating, that speciation part becomes, you know, much less valuable to you.
Thank you.
Well, thanks, everybody. Thank you, Mike, for that. That
All
was
right.
really interesting. There's some interesting questions
Yeah.
coming up afterwards as well. So thank Mike for that. If you need to talk to him, talk to him later. Thank you, Mike.